P.S. I have put up section 9.1 homework on Google Classroom. It's not due until Tuesday. We're not going to really do a lot in it today. Mostly today is kind of just mastering trig sub. Not perfectly. Not like for the AP, because it's not going to be on there. But it is a super interesting application of trig, and it is like a, wait a minute, it doesn't have trig, but we would want to bring in trig because trig is useful. Anyway, but coming back to the homework that you guys did have for today, that worksheet that was in there had way more problems than you had for homework. True? So let's pause and make sure everyone did the right homework. You guys came down here and did all the evens, right? 2 through 12? Yes. Perfect. But what was up here? Sample problems. And I kind of picked out a few of them, right? Well, the first example I didn't choose this one because I really wanted you guys to see a u squared, not just an a squared. So the first example we did yesterday had was it a 4x squared? Yeah, it had a u, because a lot of the ones in the worksheet just had x squareds, not like a number x squared. So anyway, I did this one a little bit unique, a little different. But then I started stealing them from the worksheet. This one wasn't too bad. This one, though, got a bit interesting, right? But, if this is in the sample problems, did you guys notice, okay, here's all the answers, right? But what was after all the answers? Sample problem solution. So if we talked about yesterday how number 6 needed a party to solve its secant cubedness, you guys could have come down and looked for number 6 to find the secant cubed mess. And as you got to, ¿dónde está? Here it is. As you got here, you might have been like, how did they solve? Did they solve for secant cubed at all? Well, they just filled in they must have done secant cubed somewhere earlier, because check it, they filled in a formula for it. There's a secant cubed of theta d theta integration formula? Yes. There are actually tons of integrals for tons of different expressions. There are books that are this long full of what they call integration tables. Integral upon integral upon integral with their anytime derivatives. Now, that's not truly what they did because they're a little bit snazzier than that. In example number 5, check it. What do you see them taking the integral of? This is all of their secant cubed work ending in an expression that they then went ahead and for the rest of their problems just plugged in because now they know, like a formula, hey, anytime you need the integral of secant cubed, you always get this expression. So, check it. Here's my version up here on the board. Secant cubed needs integration by parts. True? If you're wondering why there's a cute little red circle, I asked the pre-cal kids because they're learning trig identities, the basic. Honors is learning like the harder ones, like double angle, half angle, that sort of stuff. For the regular pre-cal, I was like, hey guys, do you understand anything on this board? And they found the one thing they understood. But I was able to say like, hey, Calculus BC, levels of math advanced from where you are. Trig is making impossible non-trig problems possible. Kind of cool to draw that correlation. They might not ever remember it. Maybe you guys did remember? Maybe you didn't. Probably not. But anyway, that's okay. Trig identities come back. But secant cubed, sorry, forget that red circle. That was pre-cal. Secant cubed. Why is it possible? Come on, what am I doing? Integration by parts. Why is integration by parts really helpful for secant cubed? Because secant squared can be a dv, right? Secant squared has an integral of a tangent. If I go ahead and do my ultraviolet voodoo, then I have my uv minus the integral of v du. Wait a minute, this looks like a lot of expressions. It looks like the expression on number 4. This looks like exactly what you would have gotten after like a quick plug-in or something, I think. But then you could have just gone ahead and gone again to get your secant squared minus 1. You would have gone again to get your secant cubed x minus secant of x, and then you could have looped it. The looping makes the difference, because if you can get something, now some of you might have realized, wait a minute, I could have looped it way back here if I had been a little strategic in how you did this and kept the entire expression, because you could have looped it a little bit earlier. But I'm just doing secant cubed, so I just did this. I didn't use the original expression in number 4. But anyway, you get a secant cubed right down here. Ha-ha, loop it. 1 secant cubed plus 1 secant cubed is 2 secant cubed. And then I can go ahead and just have this expression, take the integral of that expression, which is that nasty ln dude, and divide everybody by 2. Ha! Secant cubed, from now on, if you want to memorize it, you can just plug it in, plug it in. Now remember, wait, trig sub, is it on the AP? So do you have to memorize it? No. But could you from now on, once you show it once, awkward, once you show it once, they did it too. Once you show it once, can you now go ahead and use this anytime you see secant cubed? Yes. Which is nice, because in our number 6, now that I've shown it on the whiteboard, when we have to go to finishing, wait a minute, that's the one we were doing yesterday. Once we go to needing to finish, you would be like, oh, integration by parts. I know what the answer is. Let's just use it. So then I have a 9 times secant cubed. Notes open. Let's finish number 6 from yesterday. 9 times secant cubed. Oh, thanks. Sweet. 1/2. Secant x tangent x plus 1/2 ln of secant x plus tan of x plus c. Aha. So, did we have time to do secant cubes together integration by parts yesterday? No. But that's why it was a party, because you had to figure out how to do it, but once you do it once, you can then use it for any future problems that you need. So even right now, is this you're doing it once? Not unless you just wrote all that down. Which means you still have to do it once. But otherwise, you can say it's 9 halves secant x tangent x plus 9 halves ln of secant x plus tan x. Sorry, there was a plus. Dun 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 dun. Suffer once and use it to benefit and make your lives easier on future problems. How many times did secant cubed show up for those of you that persevered through the entire homework 2 through 12 and tried all of them? How many times did secant cubed? Just 2? So you show the work once, and you get to steal the answer for the other ones. 4 and 12? Nice. So, besides 4 and 12, I think this is pretty close. Sorry, this page I was going to show you yesterday, and then I didn't. There is a table. I think it's in our book. I forget what section trig sub is, but I just do the worksheets a little bit easier. It has some solutions to it. And we're not doing this for the AP anyway. We're not going super deep into it, just kind of giving you an overview. Do you see how this is pretty much what I did as far as I see this expression, I think a right triangle, I know he's my hypotenuse. Variable expressions, always opposite if I can, if it's the hypotenuse and stuff. Constant expressions, always the adjacent if I can, unless I make it the hypotenuse. And then you're using sines and tangents and secants. Like I think I pretty much gave all that to you, but there is a chart. It is nice. It is neat. Maybe you'll like it. But that's a definite one. Can we just see if you guys have any questions or any work that you don't understand or any holes that you need filled in besides secant cubed? Secant cubed, right there. Do it once, and then you're done. You can use the end result like I just did to finish. AJ.
There's some that, like, the answers, like, sine inverse.
Ooh, the sine inverse ones. Actually, I think we had, which example that we did had a sine inverse? We did one, didn't we?
Yeah, 2 of them.
Oh my goodness. I need to figure out how to make smart go faster, but not right this second. This one, I think. Yeah. Where did the sine inverse come in my example? The sine inverse came in where we had a power reducing. And because of the power reducing, which we had to use that property from pre-cal, we end up taking the integral in terms of theta of a constant, which means we get a theta in. And as soon as we have a theta, we have to go back to the triangle and say, stink, how do I get theta? Well, I can get theta, and this is the one, Kevin, was this you yesterday? Saying that there could be multiple answers? Yeah, I think so. I could find theta using sine, using cosine, using tangent. I could find theta using any of the trig, any of the six. Because I could technically say, hey, theta could come from adjacent over hypotenuse cosine inverse, or theta could come from opposite over adjacent tangent inverse, or theta could come from, ready, opposite over hypotenuse sine inverse. So we could get theta alone by taking sine inverse of the opposite over the hypotenuse and plugging in. So we could technically use any trig inverse in order to get theta alone. Did anybody notice in the answers, did they ever use anything other than sine inverse? Okay, I think it depends on the orientation, because for a different triangle, it might have been easier to do like a cosine inverse, because the x would never be done. Using a secant maybe, because the x could be a hypotenuse. My guess is the preferred one, AJ, will be the simplest one, because if you notice, tangent would use the nasty square root guy, cosine would use the nasty square root guy, sine just uses x, so it's like the simplest way. Does that kind of make sense? But you have a theta alone, and the only way to get theta alone is to come back to your triangle and use an inverse trig to get it. Good question. Anything else from last night's 2 through 12 besides secant cube, or even maybe the one with secant cube, but that's not your question. You got stuck somewhere else. We're good? Oh, 2?
I just have a question on number 4. Like, I ended up with, like, for my answer, it was like negative 25 over 2 ln of like absolute value x over 5 plus square root of x squared minus 25 over 5.
Oh, sorry, let's do the wrong answer. Hold on. Read your answer one more time. Sorry.
It was all of that except in the absolute value, it was all over 5.
Good. Did anybody else get the all over 5? Yeah, Kyrie. We should have tons of hands, because the problem is this is not the naturally occurring answer. No one else got a number 5? For number 4. Oh, we didn't finish that one? Did that show up anywhere else? Patricia, besides number 4? Would that be?
Over 5?
I feel like number 12 might have that too. I might be wrong. But maybe a lot of you guys didn't get to number 5.
What I did was, because since the secant cube involves integral of like a secant, just a secant, I kind of just combined because there's another integral of secant on the problem when I do like you're integrating this.
So you looped it so you didn't have to worry about it,
Yeah,
so
I
that it
kind of
wasn't there.
combined this.
Okay. I won't call that naturally occurring, but I will call that smart. Naturally occurring. Okay. Number 4. Can we just go to number 4? How many of you guys got stuck on number 4 and you didn't get a final? Okay. Let's talk about number 4, because then maybe you can finish your number 12. Yeah? Using number 4's strategy. Okay, so number 4. However, I'm not going to do integration by parts again because I already did it. I did. That's my handwriting. Okay. But you guys, maybe you do need to show your integration by parts. Let me go to number 4 real fast, but using the final solution of secant cube. Because Patricia, that's an excellent question. And that's one that last year, Maggie reminded me. She and Riley that day, and Kathy. Kathy had done the homework, but she got really stuck on the secant cube one, and I think James had partially done it. No one else. Well. Anyway, he knows it now. You can ask him. Play that. He'll just start laughing if I ask him to do a homework problem. No, he'll go grab the book. He's like, okay, I'll do it. And he'll start it. And then Hannah will come up with it. Anyway, it was a part. Number 4. This part that Patricia just asked was exactly when the 3 girls were like poring over Kathy's problem, trying to explain to her. Actually, Maggie and Riley figured it out. They were explaining it to Kathy as to how or where that denominator went. So, beginning problem, Patricia, help me out. What was the first thing for number 4? Integral of?
Square root of x squared minus 25.
Oh, it's just a square root? Yeah. Sometimes that secant cube guy just shows up. Sorry, it was 25 minus?
X squared minus 25.
Okay. You guys drew a triangle, and in that triangle, you knew that you had a hypotenuse, which was x, right? Is anybody not using the triangle? You don't have to. Organic chemistry, dude, totally, that's a nice foot. Organic chemistry, dude. I should say shoe, but
I'm taking a picture of your secret.
No.
I don't know, but get a nice flash. All right, so coming back. I like the triangle. It keeps everything straight in my head. We have our theta, we have our x, we keep our constant here when possible. This ends up being, now I understand what was on there. So, coming back. I can go ahead and use secant, right? X is equal to 5 secant of theta. You guys get? Oh, not d theta. We haven't done that yet. You can take a derivative pretty quickly. And you get dx is equal to 5 secant theta tangent theta d theta. I showed Joe and Lorenzo this quickly yesterday. Just a few of you might appreciate what I'm about to show you. Do you know how in all the examples I did yesterday, I would have plugged into x right now? And I would take my 5 secant theta, I'd make it 25 secant squared theta. I'd have to pull out the 25. Square root of 25 is 5. Secant squared minus 1 is tangent squared. Tangent squared square root is tangent. Couldn't we also look at this and say, I see him. And couldn't I make a trig expression out of him? And couldn't I come over here and plug in said trig expression without doing any of the work I just explained to you? Oh. But doesn't that take some creativity? Because depending on what you're given, you might not always want to go straight to that. If I give you x, you can plug x in wherever you want and however many times you want. And you can take a dx really easily. This is the beginning. But then once you start realizing, wait a minute, he's there, why not just do a tangent? And you can start being creative to jump ahead in the process. But does 25 secant squared minus 25 eventually get to 5 tangent? Yes. Okay. Wait a minute. What did I do, though, that makes it so that I'm going to be horribly wrong if I keep going? dx is not d theta. It would have been so nice. I'm like, wait, this is an easy pattern. Struggle. Was the 5 tangent of theta easy? Yes, if you look at it this way. But what do you still have? Okay, so 5 times 5 is 25, and I still have my secant theta. dx is this entire expression, right? Now we end up with secant times tangent squared. This is where the secant cube came in, right, guys? Okay, so then we had 25 times. We have the integral of secant cube theta minus secant of theta. Secant cube theta, I'm going to steal from over there, which is going to be 1/2 secant x tangent x plus 1/2 ln of secant, sorry, these are not x's though. Secant theta plus tangent theta plus c, hold on, not yet. I still have this minus secant guy who has his own integral. Minus, well, I just kept the 25 on the outside. But yeah, you're right. Minus ln of secant theta plus tangent theta plus c. So here's my secant cubed, right, from the board. Okay, here's my secant cubed from the board. Here's my, that was secant cubed integral. Here's my secant integral. The 25 on the outside. Do I have some like terms I can combine? So I have 1/2 minus 1/2, which would be, sorry, minus 1. And can't I just pull the 1/2 out at this point? If that's going to be a negative 1/2, just pull that guy out of there. So I have 25 over 2 with secant theta, tangent theta, minus, right? Minus ln of. want to be snazzy, you can just put that 25 over 2 out there. Okay. But what's the problem? Why am I not done? And why has Patricia's question not even really been fully realized? Yeah, I need to get back in terms of x. Remember, we brought in this whole in terms of theta with trig just to be able to play and manipulate and actually integrate. But we have to go back in terms of x. That was the beginning problem. So, Patricia, when you went back in terms of x, what did you plug in every time you saw a secant? Good. Coming back to the triangle, to the secant, hypotenuse over adjacent. I can make all my secants x over 5. And I can make all my tangents.
I said, no way. No way.
I have to put that inside the ln. Can I go to another line because it's going to get long? Where's Patricia's question coming from? If you guys look at the final answer right now, that is right here. What's missing inside the ln? Where'd the over 5 go? Check it. See, your ln? Isn't it supposed to be? Wasn't secant hypotenuse over adjacent? Isn't tangent opposite over adjacent? Where's the over 5? Where's the over 5? Where's the over 5? Now some of you are like, well, where's the 25? Hold on. 5 times 5 is 25. That one's fine. I have the 1/2 x square root of x squared minus 25. I have the 25 over 2. Where's the over 5? Got it? Christian, you got it?
Could you like make it ln of numerator and then over and then make it a constant and add it to the
I love what you're thinking. You made a minor error in applying formula. But yes. So Joe, correct her, well, walk through doing what she just said, just fixing the error.
It's just because the ln is subtract.
Subtract, not divide.
Because the divide.
Yeah. What property is that? So we can try to like draw the comparison in their minds as I start writing. He's saying divide is subtract. What's he talking about? Log properties from pre-calc. Or logarithmic differentiation from AB, but going back to let's do now log properties. So can't I take, okay, are you guys okay if I just look at this guy for a second? Can't I make this 25 over 2 ln of the top? What happens in any indefinite interval when we have a constant? It gets absorbed into C, right? Technically, I can make ln of A over B, ln of A minus ln of B. ln of A is a variable expression. He's going to stay. But ln of B is ln of 5. Absolute value doesn't make any difference because it's still just a positive number. But ln of 5 is a constant times 25 over 2 is a constant, and it will get absorbed into the constant. Why didn't you see that in their answer? Because we're lazy and we don't label this like a plus C1 plus C1 plus C1, and all of a sudden in the final answer put a C2. We just call it a C. But technically, was this correct? Absolutely. Why wasn't the final answer that? Because they absorbed a constant into the arbitrary constant. Or I should say into the constant of integration. That's the proper way of saying it. And so we do end up finally, after absorbing that constant, with 1/2 x square root of x squared minus 25. So was Patricia wrong when she said that she had the over 5? No. You're totally right, kid. Just as far as proper notation, that over 5 should have gotten absorbed into your plus C.
So if the AP were to ask this question, would it want us to give the answer in like the first?
If it was a long answer, you could just box it. Like if it was an FRQ part A or something. It's not going to be on, remember, trig sub, not there. But thinking about differential equations and solving antiderivatives and some of them being tricky and maybe involving integration by parts, etc., you could get to a point where you are solving for an antiderivative. They probably will give you an initial condition, so you'll be actually plugging in a final number to where this won't be a problem, meaning you could plug in and solve for an appropriate C to have this be correct. But you could also have simplified it and solved for an appropriate C that would have to be different, but also just as correct. Does that make sense? Yeah. So just because like you wouldn't necessarily need this in an FRQ, you wouldn't have had to have made that step to make it appropriate, to make it correct, because you could have solved for C1 or solved for C2 and been just as correct. But in a multiple choice answer, they won't leave in an antiderivative a constant that should be absorbed. They would have the most simplified C be the correct answer. Okay.
What is your reason for like not having trig sub on the AP?
I don't know. That's an interesting question. I think the sign inverse and how there are multiple different ways of solving it or getting to an answer. My assumption is that above and beyond all the other types of problems where there are multiple representations, trig sub, you can have it written so many different ways. And kids would have to do so much algebraic simplifying to get to one proper answer or to get to one specific, depending on what route they take. Because all of them should condense to the same answer. Unless you have like an inverse trig. So I think that variableness in the answers would make it harder or too hard on their FRQ graders. And in multiple choice, it would be too hard on the kids themselves to make that one perfect match. That's my guess. But I don't know for sure. It's a good question. But yeah, college profs would definitely teach. Maggie was saying yesterday, she's like at Berkeley, she's like, yeah, we spent a little bit of time on it. But they were also doing like a calculus for biology, and that teacher was going into like computer programming and DNA sequencing and all. That one class was pretty crazy. But she needed her A, B, and BC, and she was like, yeah, it was pretty much all review until the very end. But actually, you guys want to learn from not her mistakes, but her experience. She was like, yeah, I kind of got used to in that class just knowing what I was doing. And she's a good student, so she wasn't just like, she was doing her homework. She just wasn't having to like really study independently on her own. She's like, yeah, I kind of just got into the habit of not really having to do a lot of work. So then what happened on that last portion of that class when it got to new stuff? What was hard for her to do? She got used to coasting, she got used to reviewing, and then all this new stuff came. What was hard? Yeah, actually like putting in time, because she was used to putting in time to all these other classes, and she was used to kind of having this be like on the safe back burner. And then all of a sudden it was like, oh no, right? And she still did okay. She still did really well. But it wasn't quite what she would have wanted because she had gotten into that like, oh, I'm kind of coasting. Now, for you guys, why am I bringing it up right now? Second semester at CalcBC. Some of you have been coasting. Now, you've been working hard, hopefully, doing homework, but haven't you been like, I don't totally mind my test grades because, I mean, I know it. I'm just making mistakes. And she's grading harder, not as much partial credit, not as many questions. They're all multiple choice, right or wrong. I still get partial credit. But we've been coasting a little bit. What does trig sub mark the end of? The end of harder integration. Now, have we done integration by parts, which is new? Yes. Have we done trig sub, which is new? Yes. Have we kind of reviewed parametric and polar, which is basically just review? Yes. Have we done Euler's method and some other new things? Yes. But in the context of limits, derivatives, integrals. Right? And applications. Okay. we're about to go to something new. Now, let me make things a little easier. Ready? It could be that this one section, to some extent in other books, it should be that this one section is the beginning of the brand new. Not brand new. There are numbers, there are letters, there's something called a sigma that you kind of know who he is, but it's basically brand new. This could be the start of brand new. It's not. Let me show you what I mean. We're coming right back to this. You guys, in your Barron's practice exam, haven't you been, or didn't you already cross off anything to do with converging or diverging or a sigma? Okay. Let me show you what assignment just popped up in your Google Classroom for Chapter 9. Wait a minute. What's Chapter 9's title? L'Hôpital's. That's review. Improper integrals. Well, wait a minute. You can't fully see it. I don't know if you can. Oh, you still can't. Can you see it now? Well, okay. Sequences, that's new. L'Hôpital's, that's old. Improper, that's new. Integrals, that's old. Oh. Is Chapter 9 the beginning of brand new? No. Sequences is. But they technically let us do sequences for a bit and then say, hey, L'Hôpital's. And we're like, what? We already, okay, sure, why not? Improper integrals. An integral with infinity or a discontinuity as a bound? Okay, sure. We get to kind of have a little bit more of a break before it's brand new. But this is the section that introduces basically the bulk of second semester B. Convergence and divergence of infinite series. Series? This is sequences. I know. But it introduces it. Lorenzo, what do you see? Ah! It is a special limit. Well, that's kind of nice. Okay, sequences. Hold on, we're not even to the example yet. But yes, you're right, it is a special limit. But I'm not sure we're going to infinity. Although maybe they're trying to have us start thinking about that. Sequence, a list of numbers written in an explicit order. A list of numbers written in an explicit order. Back in pre-cal, we would say basically it's a rectangular array. Is that how we would put it? Rectangular array of numbers. Basically, number, comma, number, comma, number, comma, number, comma, number, comma. Sometimes there's a pattern, comma. Fibonacci, it's a sequence. Arithmetic, geometric, special types of sequences. How prices have risen in Bob's Snack Shack over the last 5 years. That'd be a secret. So sequences, basically a list of numbers separated with commas. It's not a sum, those are series. Just a list of numbers. Now this one, Lorenzo already gave it away a little bit and said, oh, hey, that's all right. But hold on, what would the first 6 terms be? Wait, now you have to remember things like what are terms? Terms are numbers, right? Like a first term, second term, third term. What does N stand for? In pre-cal, we would have maybe called this A sub N. You see some A sub N down here. They can call it whatever they want. Q sub N, K sub N, L sub N, I don't know. But who's N again? The term, yeah, the first, the second, third. Now be careful, the first term is sometimes the zeroth term, like when T is 0 in physics at the beginning. But, yeah, we could say N is 1, N is 2, N is 3. So if N is 1, what would my first term be? Yeah, 2 to the 1, right? If N is 2, what would my second term be? Okay, let's do it this way. How about we make it 2 to the 1, and then we make it 3 halves to the 2, and then we make it, what would the next one be? 1 plus 1 half, right? What would the next one be? 1 plus 1 third. Wouldn't that be 4 thirds raised to the 3, and then the next one would be.
5, 4.
Is there a pattern? 1, 2, 3, 4, 5, 6. But where does it get hard?
100.
Oh, come on. Some of you got hard in the second term. But yes, the 100. But yes, the 100. I wonder if there's any more of a pattern. I mean, well, wait a minute. Couldn't we jump to the 100 seeing the pattern? Because we have the first, second, third, fourth, fifth, sixth. This is the 6th. Wouldn't the 100th be 100 over raised to the... Oh, we like patterns. Maybe not. But we could keep going after that, right? What are all of these approaching? Yeah, if we were to go super crazy, but just because we memorized it, actually we kind of even saw how it occurred. It does approach E. That's super interesting. But just a quick reminder, there are 2 different ways of defining sequences, right? One is explicitly, which means just give me a, oh guys, you could have just plugged in 100. It wasn't that big of a deal. We didn't even have to find a pattern. The pattern is this, right? That's explicitly defined. What's this one? Implicit is one way of saying it, but computer programmers would probably call it recursively defined. Not evil, just tell a calculator that, and it can go ahead and tell you whatever term you want. Oh wait, it's a mode in your calculator called sequence mode, SEQ, where you give it a first term, you give it a formula for the second or the next term, and then it can find it for you. Even recursive ones, because computers can make those jumps super fast. Do you remember how recursively defined sequences work? What would my first term be? 3. That's easy. They gave it to me. A sub 1. Remember, subscripts are the placement of the term. But what would my second term be?
1.
Ah! Because you figured out from this nasty notation, it's not that bad. It just says take the guy before and subtract 2. Oh, so what would the next term be? And then? Ah! 8! Okay, hold on. So then I have to do -5, and then -7, and then -9, and then -11. Oh, okay. Whew. Got it. What would you really not want them to ask next?
100.
Which is why we have computers, because they can do things like that over and over and over again. Do annoying repetition. Unless, maybe we wouldn't need a computer if you wanted to use your calculator and keep track of how many -2s you were doing. If you figured out a way to use a pattern to make an explicit formula to plug into the 100. What could be an explicit way of getting from 3 to 1 for the second, to -1 for the third, to -3 to the fourth, to -11 to the 10th, and then, oh, so you start with this. Every time you're doing -2, but how many -2s are you doing? Well, for each placement, second, third, fourth, fifth, you've done 1 fewer jump of -2. Is this maybe something that's coming from special explicit formulas for arithmetic sequences? There are some patterns that exist for arithmetic and geometric, arithmetic if you want to be snazzy, and geometric sequences. There are other explicit formulas that can be made, they just get a little bit harder. But if you can make it explicit, or if you can deduce or determine a pattern that lets you jump straight to an answer, well then they ask you something like, what's the 100th? Just introducing, reminding you guys of notation and stuff too. Of the 100th term, you're like, well that's not a big deal, it's just 3, and then how many jumps of -2 did you do? Well 99 -2, so then just do 99 -2s, which would end up subtracting 198, right, from 3? Which I believe would give us -195. Someone back me up on that. Cool. Patterns. Patterns are power? I don't know if I go that far. But being able to find patterns will definitely be helpful. But don't worry. You don't have to be super, super, super creative. There are definitely structures in place that we're going to be able to follow as we go through series S. Series are the point of second semester. Sequences, though, are how we get to series and how we introduce. So, guys, what we're going to do tomorrow is play around with arithmetic ones. We're going to play around with geometric ones. We're going to play around with making sequences. It's a lot of just like, oh, hey, that sequence mode. It might be helpful for some discovery stuff that we do. After we get out of our chapter 9 into another book's chapter 9, that's where we go after the next test. But then we start. Just start! Talking about the word conversion of sequences, not series. Convergence of series is going to take us 2 chapters to cover, and even then, well, we'll see how that goes. With that, you guys have 35 seconds to hang out and have fun. Tonight, what would I do? Me? I think tonight I would just do Barron's. Finish up Tricks. Reminder, what's due on Monday? Barron. Bye, guys. Get out of here and get to the lunch line early. I'll see you guys later. Be quiet in the hallway.